So we want to talk about another idea of what we can use the derivative of a function for to describe what's happening in a graph. And so to see this, we're going to look at two graphs and notice how they are different. So we have the following graph. We have the following two graphs, I should say. Now notice both of these graphs from A to B are increasing. They're both going up. But it's inaccurate to say this one should look a little bit more like it's actually always going up. It's inaccurate to say these are really the same kind of graph exactly because they're bending in different ways. And we want to describe that bending idea. And so one way of describing this bending idea is notice if we draw tangent lines, what is happening. So our tangent lines here on the first graph all lie below the line. So here, the tangent lines are below the curve. Where if we draw tangent lines in the second one, all of our tangent lines that we would have are going to be above the curve. So our tangent lines are above the curve. And so this is kind of how they differ. They differ based on where the tangent lines lie. And now we have names for these two types of situations. And so when the tangent lines all lie below the graph, we say that we are concave up. So we're concave up if the tangent lines are below the graph, and we are concave down if the tangent lines all lie above the graph. Now, to see where the naming comes from, one way of seeing it is if you think of concave up, if you draw an upward-facing U, so it's opening up, that is concave up. And if you actually draw tangent lines, you'll see they're all below the curve. And concave down is a downward-facing parabola. So since it's opening down, that's what corresponds to concave down. So if you think of how it compares to a parabola, that can help you keep straight whether you're concave up or concave down. And so this is what we call the idea of concavity. And so it has to do with if the tangent lines are above or below the graph. But we want to talk about how could we actually measure this using the derivative. Because if we have the graph, we can draw tangent lines and kind of figure out if we're concave up or concave down. But we want to do better than that. And so what we're going to do is we're going to notice what's actually happening with these tangent lines. And so in a concave up graph, I'm going to redraw concave up just to make it a bit bigger. And so this is a concave up graph. Notice that as I draw these tangent lines, what's happening to the slopes of the tangent lines. So in this concave up situation, the slopes of the tangent lines are getting bigger. And this can be a little bit easier to see if you think, well, we're almost flat like at the very bottom. Like if it's a parabola, you're flat at the bottom, and they're getting bigger and bigger as you're going up the side. And so the slopes of the tangent lines are increasing when the graph is concave up. So if we're concave up, the slopes of the tangent lines are increasing, or in other words, f prime of x is increasing. Well, we know that that then means its derivative is positive, so the second derivative is greater than 0. Since f prime, the derivative is increasing, its own derivative, so the second derivative must be positive. And similar to this idea, if we look at a concave down graph, so if we draw increasing, The reason why is the tangent lines are positive, so it's a bit easier to think about what's happening with the tangent lines if they're all positive. So here, if I draw my tangent lines, notice that the tangent lines are becoming more and more flat. And so we have tangent lines that are then getting smaller and smaller in values when we are concave down. And so when the graph is concave down, the slopes of the tangent lines are getting smaller or they are decreasing. And again, you can do this in the negative case when you have negative slope tangent lines. It's just you have to remember there you're getting more negative, which does still technically mean you're decreasing. You're just getting more negative, so the values are still getting smaller, even though you get steeper lines. And so this then means that the derivative, f prime, is decreasing, or the second derivative is negative. And this then is how we check for concavity using the derivative, is this fact that we have just noticed. So to state it a bit more clearly, this is called the concavity test. So the concavity says we're going to let f be a twice differentiable function. That just means you can take the second derivative twice and it makes sense. And so first, if the second derivative is greater than 0 on an interval a to b, then f is concave upward on that interval a to b. And if the second derivative is less than 0 on an interval a to b, then f is concave downward on that interval a to b. So you're concave up if the derivatives are positive, and concave down if the derivatives are negative. The second derivative is negative. So if we just look at a graph, kind of to reiterate this point, if we have the following function, which I'm drawing this kind of dramatically to make it clear what's happening. If this is our point A, and this is 0, then in this graph, how we have it, we have that we are concave up, because we're concave up since we're shaped upward from 0 to a, or that tells us the second derivative must be greater than 0 on 0 to a, and we're concave down on a to infinity. Or in other words, the second derivative is less than 0 on a to infinity. And so that's kind of the idea of what's happening graphically with concave up and concave down, and how it relates to the derivative. Now, similar to the idea that we had with critical numbers, we also have this idea of where the concavity changes. And so that has a name. And so a point P on a curve y equals f of x is called an inflection point if f is continuous at the point P and the curve changes concavity. Changes from, we'll phrase it differently, changes from concave up to concave down. or concave down to concave up. So if you're changing concavity, changing from concave up to concave down, or concave down to concave up, then that is an inflection point. Now, this is slightly different than critical points, or critical numbers, and the difference is coming from the fact that with inflection points, you do have to change concavity. So a critical number may not be a local minimum max, but an inflection point is a little bit different in that it is a place where you actually are changing. And note, this is kind of where they really become similar, is that at an inflection point, the second derivative of x equals 0 or does not exist. And so this comes from the intermediate value theorem again. To change signs in the second derivative, you had to have crossed 0 if you were continuous, or you just might not have existed. And so we check for inflection points by looking at the second derivative, seeing where it is 0, and doing much the same thing that we did before. And so we're going to do an example of this, but the process, you'll notice, is very similar to the process that we went through earlier. And so let's look at an example as follows. So we want to discuss the curve y equals x to the fourth minus 4x cubed with respect to concavity, inflection points, and also we are going to talk about increasing and decreasing. Okay, so we're just going to kind of analyze everything about this curve, y equals x to the fourth minus 4x cubed. And so to start with, what we're going to do is we're going to take the derivative. So we have our function f of x is x to the fourth minus 4x cubed. So if we take the first derivative, we're going to 4x cubed minus 12x squared, which this factors as 4x squared times x minus 3. Then if you take the second derivative, we're going to get 12x squared minus 24x, which factors as 12x times x minus 2. Okay, and so what we want to do is we want to analyze increasing and decreasing, as well as concavity and inflection points. So I want to start with what we've been talking about with increasing and decreasing. So we're going to start with increasing and decreasing. So that means we're looking at the first derivative. And so our critical numbers are x equals 0 and x equals 3. And so looking at x equals 0 and x equals 3, we can set up our table. So we're going to have from negative infinity to 0, from 0 to 3, and from 3 to infinity. And so then we have our test point. Then we have what is f prime doing. And then we have what is f of x doing. Okay, so on negative infinity to 0, we're going to pick negative 1. 0 to 3, we'll pick 1. 3 to infinity, we will pick 4. Now we plug these values in. So we have 4 times negative 1 squared times negative 1 minus 3, which is negative 4. So this is 4 times 1 times negative 4. So we've got 16. So we're going to be decreasing on negative infinity to 0. Now plugging in 1, we have 4 times 1 times 1 minus 3, which is minus 2. And so plugging minus 2 in, plugging 1 in, I mean, you get negative 8. So we are also decreasing here. So we're decreasing on 0 to 3 as well. And now plugging in 4, we have 4 times 4 squared times 4 minus 3, which is 1. So this is going to be 4 times 16, which is 64. And that's positive, so we are increasing. So we're decreasing on negative infinity to 0 and 0 to 3, then increasing on 3 to infinity. Now, one thing to note is when you don't change signs, we typically do and just kind of use them together. So I'm going to write decreasing as negative infinity to 3, and then increasing as 3 to infinity. The reason why is we didn't change signs at 0, so even though it's a critical number, we usually just lump it in with decreasing, and technically would just mean, well, we're not going up there. So we're using kind of a less strict definition, although the more correct way would be to write negative infinity to 0 union 0 to 3. I'm just combining them, as you will sometimes see that in mathematics, and so it's helpful to be aware it can be written either way. Now, one thing to note here is that does tell us that 3 is where we have a local minimum, because we want decreasing to increasing. So there is a local min at x equals 3. Okay, so this is just what we were doing before with increasing and decreasing. Now we're going to switch gears to concavity, but you're going to notice that it's going to be very similar to what we just barely did. So now we're looking at concavity. So with concavity, the first thing we want to do is we want to look for potential inflection points. And so these are just places where the second derivative is 0 or does not exist. They aren't necessarily inflection points, as we might not change concavity there. So looking at the second derivative, which I'm going to write down here just for ease, it's 12x times x minus 2. So our potential inflection points are when x equals 0 and when x equals 2. And so now, just like we did for increasing and decreasing, we're going to create a table and figure things out from the table. So we have our interval, we have a test point. Now we're going to plug things into the second derivative. And then we have what's happening with the concavity. So the first interval is negative infinity to 0. The next interval we're going to go from 0 to 2. And then we have from 2 to infinity. Picking out test points, we'll pick negative 1, 1, and 3. Just picking easy to plug in points. Now plugging in negative 1, we have 12 times negative 1 times negative 1 minus 2, which is minus 3. So we're going to get out positive 36. And so we are concave up on this first interval. So we're concave up on negative infinity to 0. Plugging in 1, we get 12 times 1. Then 1 minus 2 is minus 1, so we get negative 12. That's less than 0. So we are concave down on the interval 0 to 2. Then plugging in 3, we have 12 times 3 times 3 minus 1 is 1. 3 minus 2 is 1, so we get 36. That's greater than 0, so we are concave up. So we see that we'll concave up on negative infinity to 0 and 2 to infinity, and concave down on 0 to 2. So let's write that down. So we'll concave up on negative infinity to 0, union 2 to infinity, and we'll concave down on 0 to 2. So this then tells us our concavity, but what we cared about also was inflection points. And so the inflection points are places where we changed directions of concavity. And we did that twice. We will concave up from negative infinity to 0, then we want to concave down. So we're going to have an inflection point at 0. So we changed directions at 0. Then we also changed directions at 2, and so 2 also is a place where we have an inflection point. And then to get the actual inflection point, you plug it into the original. So we'd have 0, f of 0, and then 2, f of 2. Plugging it back into the original function f. Now, the original function f, if you don't recall, was f of x equals x to the 4th minus 4x cubed. So we're just going to plug these in. So if you plug in 0, you get out 0, and if you plug in 2, you get 16 minus 32, so you get out minus 16. And so our inflection points are 0, 0, and 2, negative 16. Now, this whole process is very similar to the process of increasing and decreasing. As we just barely saw, we did much the same thing in both situations. Now, I do want to mention that you can actually use the second derivative to figure out where you have a local minimum or local maximum. And so this is what is called the second derivative test. Now, what this says is we're going to suppose f double prime is continuous at a critical point, or near a critical point, C. Okay, so around that critical point, we are continuous. Basically, that just means the second derivative doesn't have like any holes or things around the point C. And so first, if f prime of C equals 0, which that is like part of being a critical point, is either is 0 or does not exist, and the second derivative is greater than 0, then f has a local minimum at C. And second, if f prime of C is equal to 0, and the second derivative at C is less than 0, then f has a local maximum at C. And so this is called the second derivative test. Notice that we do have to have that the first derivative is 0 there, so this doesn't work if the first derivative does not define there. And the reason for that is if the first derivative isn't defined at C, the second derivative won't be either. I'm not going to really justify why that's the case, but remember that if you take a derivative, you get a potentially smaller domain, so the second derivative's domain will be even smaller than the first derivative's. And so if it didn't exist at the first derivative, it wouldn't for the second derivative. And so we only are really checking when the first derivative is 0, and if the second derivative is greater than 0 at that point, you have a local min, and if it's greater than 0, less than 0, then you have a local max. This sometimes can seem backwards to people, but a good way to think of it is if you think of a parabola, well, a parabola is always concave up. So in other words, the second derivative is always greater than 0 here, and we have a local min. Where if we think of something that is always concave down, here the second derivative is always less than 0, but we have a local max. So if you go back to the parabola idea, you can kind of keep straight which one is which. Now, the second derivative test in Calculus 1 is admittedly not really helpful. The reason for this is if you could figure out when the first derivative was 0, you could probably just use the first derivative test just as easily. And so this does have its uses, but it is somewhat limited in where the second derivative test really becomes applicable. That being said, we are going to look at an example. So let's look at an example of using the second derivative test. So we're going to look at the function f of x equals 2x cubed minus 2x plus 11. And we want to find where f of x has local min/max values. And so what we're going to do is we're going to use the second derivative test to do this. So we need to take both the first derivative and the second derivative. The first derivative is going to be 6x squared minus 2, and the second derivative is going to give us 12x. And so from this, we need to find where the critical numbers occur. And so our critical numbers are when the first derivative is 0. So we want to know when a 6x squared minus 2 equals 0. This is when 6x squared equals 2. So x squared needs to be equal to 2 over 6, or 1/3. So that tells us x is going to be plus or minus the square root of 1/3. Okay? And so plus or minus the square root of 1/3, which can be written as plus or minus 1 over the square root of 3, those are critical numbers. Okay, so I'll write that down. So our critical numbers are x equals 1 over the square root of 3 and negative 1 over the square root of 3. And now we're going to use the second derivative test, so we're going to plug these into the function f double prime. And so f double prime, well, f double prime is just 12x. So if we plug in 1 over the square root of 3, this is going to be 12 over the square root of 3, and that's greater than 0. And if we plug in negative 1 over the square root of 3, this is going to become negative 12 over the square root of 3, which is less than 0. And so we have a local min at x equals 1 over the square root of 3, and a local max at x equals negative 1 over the square root of 3. Now, we can actually plug these into our function f of x equals 2x cubed minus 2x plus 11 to get out the value, but I don't know that that's all that instructive. It's going to look kind of awful because 1 over the square root of 3 is kind of an awful number. But the point here is that it was very easy to check the sign of the second derivative. So the second derivative is somewhat easy to actually compute the sign of, because it's usually going to be simpler than the first derivative, which is one advantage that the second derivative test does have over the first derivative test. And then one last thing we want to mention is we can sketch the graph of a function using the information about derivatives. So we want to sketch a possible graph, I should say. A possible graph of a function f that satisfies the following conditions. So condition 1, the first derivative is greater than 0 on negative infinity to 1, and the first derivative is less than 0 on 1 to infinity. Second, the second derivative is greater than 0 on negative infinity to negative 2, union 2 to infinity. And the second derivative of x is less than 0 on negative 2 to 2. And then third, the limit as x goes to negative infinity of f of x is negative 2, and the limit as x goes towards infinity of f of x equals 0. So we want to sketch a graph that satisfies all of these conditions. Now, the first condition is telling us that we're increasing from negative infinity to 1, and we're decreasing from 1 to infinity. Condition 2 tells us we're concave up on negative infinity to negative 2 and 2 to infinity, and we're concave down on negative 2 to 2. And then the third condition is telling us about horizontal asymptotes. So we have a horizontal asymptote to the left at -2 and to the right at 0. And so let's sketch this idea. And so it's usually easiest to draw the horizontal asymptotes first. So we know we have a horizontal asymptote at -2 on the left. And so the graph to the left is going to have to be increasing and concave up, because it's concave up on -3 to -2, but it has this horizontal asymptote. So the graph to the left of -2 looks kind of like this. Now we need to be concave up on -2 to 2, but we have a local max at 0, at 1 I mean, because we changed signs from increasing to decreasing there. So we need to stay concave, we need to be concave down. Let's see if I can draw this a little bit nicer. So we'll concave down from -2 to 1, but we stay concave down until we get to 2. So we stay concave down until 2, and then we need to have a horizontal asymptote at 0 and be concave up, so the graph looks like the following. And so this is a sketch of the situation. And notice that we worked kind of our way from left to right, just meeting the conditions. And that tends to be the way to sketch a possible graph using the conditions. Draw in the horizontal asymptotes that you know, and then use where you're increasing to decreasing and concavity to move from left to right.